Folks, my name is Rhy McMillan, and I just recently graduated from UBC with a PhD in geological sciences. And much of my dissertation research focused on investigations of materials from the archaeological record, including some absolutely fascinating microbelongings from the village site of Musqueam. And those microbelongings are composed of a very familiar material, perhaps to some of you. It's volcanic glass or obsidian, or if you're a Game of Thrones fan, it's often called dragon glass. And just as it was important, and especially in the later series or seasons of that particular series, it was also likely highly valued by ancient people. And that's because obsidian, even today, still makes one of the sharpest edges that humans can manufacture. And in the past, this meant that very quickly and very readily, you could create a very sharp stone tool. But in addition to that, because it was so brittle, allowing it to become so sharp, it actually needed a lot of resharpening, and thus ancient people would have had to procure a lot of this material from the landscape in order to be able to use it frequently. And luckily for archaeologists, that plays into an integral part of investigating how humans interacted with the ancient landscape. We want to find materials that they used frequently and often and identify from where they originated to see where ancient humans went or with whom they interacted. So not only is obsidian good because it produces a lot of material in the archaeological record, relatively speaking, but it also, hidden within inside every piece of obsidian, is an answer to the question of where. And frequently, archaeologists would use trace element concentrations alone to identify from where these particular objects originated from in the landscape. So they would take an obsidian belonging, they would analyze it for trace elements, and they would compare it to source materials from different volcanoes that produced obsidian and try to match obsidian with those sources. And while that works relatively well, unfortunately, it doesn't quite tell the whole story, and it wouldn't have necessarily helped with the story that I'm going to tell about these Cessnom belongings. So one of the main challenges with using trace elements is that concentrations of an obsidian flow are not necessarily unique. So it's not actually scientifically possible to say that a belonging came from a particular source with 100% certainty without knowing that we've analyzed all of the sources in the world and we can exclude all of them. So making positive attributions using trace elements alone is not actually scientifically feasible. The second challenge is that trace elements vary on each actual eruption of obsidian, right? So you can connect an obsidian belonging back with a particular flow or an eruption on the landscape. However, most volcanoes contain multiple of these eruptions, and those were most likely eroded together to be collected by people from the same location, meaning that the flow resolution might actually put too much precision or accuracy on archaeological interpretations of this data. And the major catch out of all of this is that we can never actually prove that a belonging came from a source, and we can only exclude possible sources. And that's important because by using trace elements, we have to exclude all of the flows that exist out there, and we don't necessarily know where to start all the time. Right? We have to go systematically by excluding these flows, and we'll never know if we've analyzed every flow of obsidian. So what we've done as part of my dissertation research is try to find multiple lines of evidence that can be used to exclude as many sources as possible when doing obsidian sourcing in British Columbia. So of course we use trace elements, but we've also adapted a technique that looks at the molecular structure of these glasses, which tells us perhaps how hot they were when they cooled really quickly, as well as a bunch of other information about their major and minor element compositions. And that can also be done non-destructively, just like portable X-ray fluorescence of the trace element composition of these obsidians. So we can collect now two independent lines of evidence without destroying these belongings whatsoever. In addition to that, we can use lead isotope ratios, which actually are indicative of where the magma came from that produced the lavas that eventually produced these obsidians. And those vary not on the obsidian flow level, but on the spatial scale of actual individual volcanoes, which means that if we get the lead isotope composition of a particular obsidian belonging, we can tell which volcano it came from in BC. And then from there, we can narrow down systematically which flow it came from. In addition to this, the lead isotopes within British Columbia and obsidians that have erupted along the coast, they actually decrease systematically northward. So the ratios of heavier to lighter lead isotopes actually decrease as you go from south to north in BC, which means that if you give us a piece of obsidian and we analyze it for lead isotopes, we can tell you approximately which latitude it erupted from in the province, which is super cool. The challenge with collecting lead isotopes, though, is that we typically need to destroy the object that we're analyzing in order to be able to analyze it, right? We break it down into its constituents parts, and then we count the relative abundances of those parts, in this case, those parts being isotopes. But we've developed a way to collect just as good of information with only basically making a pinprick in these belongings. We call our procedure splitting obsidian because we take an obsidian belonging, we put it in a little tiny chamber and shoot a high-powered laser at it. Now this laser, it's actually ultraviolet, you can't see it, and it excavates an extremely tiny amount of material. So this is about 10% wider in diameter than the sharpest point of a sewing needle, which is an extremely small, practically invisible spot. But that's enough material that we can actually sweep that substance into a mass spectrometer and count the individual parts in it, allowing us to obtain lead isotope ratios, which we can use to match with volcanoes. So by doing this in obsidian belongings, we actually are able to provide more robust information about which volcano an obsidian belonging came from without destroying it further. And if we don't want to analyze everything in an assemblage, which is often the case, because this is still technically not non-destructive, it is minimally invasive, there will be a tiny amount removed, we can analyze representative samples from an assemblage of artifacts or belongings that we've been able to establish based on the non-destructive techniques used at the beginning of the procedure that I mentioned before, that being portable X-ray fluorescence and Raman spectroscopy. And we were able to apply this approach to a very fascinating set of belongings, what we've actually called micro-belongings, that were found mixed in with groundstone beads in the deposits at Musqueam. And these micro belongings, although they're, barely over half a centimeter in width in most cases, we couldn't actually analyze them with portable X-ray fluorescence because they were too small. So we were stuck a little bit with this problem of how do we apply this procedure to something so small and still get meaningful outcomes without destroying these belongings? Well, our splitting obsidian approach works perfectly for this. And the first step was looking at the structural characteristics using a non-destructive technique, so Raman spectroscopy. And what we found is that 4 of these micro-belongings, in total there are 12, 4 of these micro-belongings were composed of a particular type of obsidian that had a lot of the mineral magnetite in it. Now that mineral magnetite is not common in obsidians from the Pacific Northwest, so it prompted us to start investigating elsewhere where we might be able to find obsidians that have this particular characteristic, because these appeared not to be local. Whereas the remaining 8 belongings, they all, or in this case, let's say 9, there's 13 in this plot, they all ended up plotting along with the Cascade volcanoes and the Garibaldi Belt volcanoes from the Pacific Northwest. So we expanded our search for these 4 particular rogue belongings to see where they might have actually originated from, and we had a feeling it was from quite far away. So we started investigating sources farther down south in places like Idaho and Oregon to see if we might be able to systematically exclude those as well. Now, when we analyze these micro belongings with laser ablation, ICP-MS, which is the technique with the pinprick, we actually didn't just collect lead isotope ratios. We actually took the amount of material that we obtained from these belongings and split it into 2 separate mass spectrometers at once. One collecting trace element concentrations, so we could compare those with the volcanic sources, and one collecting lead isotope ratios, so that we could collect those with, compare those with the volcanic sources. And this allowed us to look at lead isotopes first. And if you remember from a few minutes ago, I mentioned that lead isotopes vary on the volcanic center scale. So by looking at the lead isotopes, we're able to show that, again, these magnetitic belongings, these ones with the really weird structural characteristics, they have completely different isotopic compositions than those materials in the Pacific Northwest, the volcanoes that produce obsidians there. The rest of the belongings we analyzed, of course, matched with the Cascades and the Garibaldi Belt, so presumably they're rather local. At least they're not from the interior of the province. They're probably from somewhere in Oregon or something like that. But those magnetic belongings fell completely off of the lead isotope space for the Pacific Northwest, meaning that we needed to look further south. And in this case, it led us to the Browns Bench obsidian deposits on the Snake River Plain in the Yellowstone Volcanics in southern Idaho. And then when we looked at the trace element concentrations of these obsidian belongings, they also showed that we could not systematically exclude Brown's bench for these magnetic belongings, and we could exclude all other sources except for the Oregon sources for the other belongings that we analyzed with the circle markers there. This allowed us to postulate a landscape use vector, so a transport vector of over 1,000 kilometers long southeast from Susqueam all the way down to southern Idaho. If you see in the background on this figure here, I've drawn in some ethnographically documented trade routes, which are particularly interesting to note how close they come to Brown's Bench. And the other belongings that were mixed in with these magnetic ones either came from obsidian cliffs or glass buttes in Oregon, as far as we can tell. So we were able to exclude all sources except for these. These are not definitive sourcing outcomes. As I mentioned before, it's not scientifically possible to prove that these came from here. But what this does is it provides a really robust argument that these belongings came from so far away, and that they can be used as additional lines of evidence to support the oral documentation of these previously known trade and exchange routes that were used by Musqueam in antiquity. With that, that's kind of the main cool part of the story. We've got these really ancient and really, really distant belongings that we've been able to analyze without destroying them. And hopefully soon we'll be able to put something together and keep sharing this wonderful outcome with the rest of the world. So thank you very much for both listening to me now and for giving me the pleasure and honor to work on materials from within your territory and work with such lovely folks as yourselves. And I hope you have a great day.